Hi, and welcome to my series on production grade systems development. My name's Dave Oram, and today I'll be walking you through our discussion on our data layer and databases. If you're new to this video series, I encourage you to go back and have a look at my previous videos, which will set the scene for this one. If you want to follow along, point your browser at github.com/davidoram/beaker. Otherwise, you can just watch along on the video and I'll cover all the steps. It's worth taking some time and care when to understand your data and model it correctly. That's because data is the foundation of any application. Systems come and go, but data lives for a very long time. And often you'll see an application that might be built 20 years ago, and the data is migrated, even though maybe new applications are built on top of that same data. So data is at the core of any application. In our scenario, we're building our stock keeping API. So data is in the form of products, SKUs, and quantities. The process that I use when I'm modeling real-world data is to try and map it onto standards and existing domains. I don't know much about product SKUs, so I did a search online to see if there was a standard representing SKUs. I couldn't find one, so I designed a data type that I thought represented what I thought was reasonable. A string between 1 and 64 characters long, containing alphanumeric characters, hyphens, and underscores. My thinking here is things like spaces are not generally used when using identifiers, so we don't allow them. Why? Because if you can imagine, if you had two SKUs, one would be A1 and another would be space A1. If you're looking at those two things on screen, yes, they're unique at the database level, but it'd be really hard for a normal user to kind of see the difference and identify them as being different. To take another example, imagine if our system modeled some kind of telephone number, maybe for our users. There is a standard E164, and that's defined on Wikipedia. So if I wanted to store a number, I would follow this standard. Why? Because I know that the data from systems often needs to interact with other systems. And if I follow the standard, it's more likely that another system's followed the standard and will be able to interchange data very, very easily. Data interchange is a really important measure of how useful your system can be when it integrates with the rest of the world. Anytime we can interact with data cleanly and not lose anything, we're kind of adding value to our system. There's standards for all kinds of data, for example, names, addresses, and so forth. I encourage you to have a look online when you're designing your system. Wikipedia might be a good place to start looking. Many applications these days appeal to a very global audience. So if your data structures can cope with that stuff right from day one, then you're at a real advantage. The other data that we'll be modeling in our system is stock levels. So I did some intense consultations with their business experts, i.e. myself, and they told me that there's no upper bound for stock levels, but they can never fall below 0. We don't sell fractions of a SKU as well, so stock levels are best modeled as an integer values that are greater than or equal to 0. Because we've started to get a good understanding of what our data is, we can now use that information to map that data onto our application. The lowest level of our data management is our Postgres database. Why did I choose Postgres over some other alternative like MySQL? Well, it's just based on my experience really. I've had many years experience with Postgres and I've found it to be very safe, very reliable, performant, and widely adopted. Remember the Bible says, "Store up for yourselves treasures in heaven where moth and rust do not destroy." And Postgres has some of those kind of values for me because it's very safe and reliable. In the previous video where we set up the dev environment, I showed how we create Postgres inside our Docker environment. And we're using the latest version of Postgres, which at the time of writing is version 18. If you open the make file, find the create DB target, it shows you exactly how we create that database. So let's go through some of the options and see what they mean. First of all, with owner Postgres. That makes the SQL role, Postgres, the owner of the new database. Encoding UTF-8 ensures that the database uses UTF-8 character encoding. That makes it useful for any kind of internationalized languages. The LC locale value, enus.utf8, LC type enus utf8, defines locale settings for string sorting, which is called collation, and character classification, or C-type. So what this means is that sorting and comparisons are case insensitive for ordering purposes. So in the sense, a capital A and a lower a are considered equal when you're sorting. So they'll group together. But equality checks are still case insensitive. So capital A is not equal to a lowercase a. Template 0 creates the new database using the template 0 database as our basis. That's a minimal, empty database which has got no extra extensions, locale settings and so forth. So what that means is we're not going to accidentally inherit some value that we don't want. Okay, so we've got an empty database, but how do we create all the tables, indexes and the other structures that we need inside the database so it's ready to be used by our app? We use a tool called SQL Migrate to create all the tables, indexes and other structures inside the database. That uses a series of SQL files and it applies them in the correct order. It manages which ones have been applied and it will apply new ones when we add them to the system. So what we end up with is a scripted way of creating a database with all its tables, indexes and so forth. SQL Migrate works with databases other than Postgres, and it also provides functionality to do things like reverse a migration. So if you created a migration and it failed somewhere, you can reverse it out and see what's going on. Okay, let's look at running a migration. We actually did that as part of the last video, but we can do it again by running make bootstrap, which will recreate the database and rerun the migrations. Let's look at the SQL migrate command. The up option tells it to apply any migrations that haven't yet been applied to the database. The --config, db.go option points to the configuration file. That tells SQL Migrate how to connect to the database. The third option, --env, specifies the environment, which in our case could be development or test. If we look in the config file, there are two sections, one for each environment. And under that options, it tells SQL Migrate the dialect, which dictates the database specific behavior, data source, which is how it will connect to the database. The dir option tells SQL Migrate where the migration files are that it needs to run. And the table option contains the database table where it will record which migrations have been run before. Let's look in the DB migrations directory to see what files it's executing. There's only one file in there. The strange file name shows the date and time smashed into the file name itself. The order that you see the files appear in VS Code is the same order that SQL Migrate will apply files. Open the file and you'll see some SQL commands and some comments. There's some special comments. 1 + migrate up indicates the block that contains the SQL when SQL Migrate is running the migrations upward, and then plus migrate down specifies the block where if it has to undo those same commands, that's where you put the SQL in to do that. We're migrating up, so let's focus on that block. Our system has a single database table called inventory with 2 columns. The product SKU, which has type text, that's the appropriate data type to hold strings. We've made it not null in the primary key. By making it not null, we prevent any null values from being stored in that column. So we only have strings, and by making it the primary key, Postgres will automatically add a unique index onto that column, which enables kind of super fast lookup when we're looking for an exact match. Next column is the stock level, defined as an integer, also not null. Now we have a section on database constraints. A database constraint is a rule that the database will enforce on a table or column to ensure data integrity. Basically, it will stop any invalid data that doesn't meet the constraint from being entered. The constraint on our inventory stock level is to make sure that the stock level is never negative. So, if someone tried to insert -5, the database will reject it. The inventory product SKU format constraint ensures that the product SKU only contains lowercase letters, numbers, hyphens and underscores, and it's between 1 and 64 characters long. This prevents invalid SKUs from being entered, those that fit outside of those rules. Constraints like this are the first line of defense for keeping our database correct and predictable. With constraints, the database itself guarantees correctness no matter how the data gets inserted or updated. The data might be inserted by an application, by a migration script, but the rules are defined at the database level and they're very efficient to run because they run inside the database right next to the data itself. Okay, let's check the database is working right. I'm going to use my database connection tool called PGX. That's an app that runs on my Mac and it's going to connect to Postgres that's running inside the code space. It can do that because in the previous video we saw the dev container was configured to forward port 5432, which makes it possible for something running on my Mac to connect into the dev container and then into Postgres. Let's test some inserts. Let's load 100,000 rows into our database and check how the query performance works. First of all, we're going to run this SQL snippet that will insert the data. Now let's select one row from the table. Let's do a select star from inventory where product SKU equals SKU 58991. That's just a SKU that I chose at random. For me, it's taking about 50 milliseconds, which is perfectly fine for development. If we're in a real production scenario and Postgres was running, say, on AWS hosted machine, then it will be much faster. But this is fine for development purposes. Okay, that concludes the lowest layer of our data management in Postgres. Now we're going to move up a layer and talk about how our application manages that data. Our application is written in Go, so the first thing we need to do is connect Go to the Postgres database. We're going to start walking through the main part of our application, but I'm really going to focus just on the parts that connect the Go app to Postgres. We're going to skip over a bunch of the other stuff. So let's start in command/main.go. In the imports, you'll see that github.com/jaxc/pgx/v5/pgxpull is imported. So PGX is a database driver that allows Go apps to run SQL against Postgres. It's not the only one, but it's one that I've used a lot. It's very mature and reliable, which is why we're using it. Note that we're using the PGX pull module, which provides a connection pool. When designing high performance applications, they might get many requests at once. Each one of those requests requires a database connection. So we want to control or limit the amount of concurrent connections. We don't want to overload our database by using too many connections at one time. It improves performance by maintaining and reusing a pool of open database connections instead of opening and closing a new one for every operation. The pool automatically creates and destroys connections as needed, and it allows us to limit the maximum number of concurrent connections in use at any one time. Okay, enough about our sidebar about PGX. The first line, context, cancel equals context with cancel, is somewhat related because this context permeates throughout the code. In Go, a context is an object that allows you to manage deadlines, cancellation signals, and contains request scoped values across API boundaries and Go routines. It allows you to control the life cycle of operations, such as shutting down gracefully, timing out, or propagating a cancellation, which is especially useful in concurrent and networked applications. Contexts help us coordinate work and resource cleanup, making our programs more robust and more responsive to external events. We'll be touching more on context as we walk through the code. The next line is set time zone to UTC or exit. This just sets the time zone of our application to run in UTC, which stands for Coordinated Universal Time. It's the primary time standard the world uses to keep our clocks consistent. Think of it as like a baseline time zone with no daylight savings, no regional offsets, just a stable reference clock. The rule of thumb when developing apps is to process and store any times in UTC and then convert those to local time only when presenting to the user. Now, our app doesn't store any times, but this is an important consideration for most apps where this would probably happen. Clicking through to the get options takes us to where the command line arguments are passed. We always have the database connection details passed in at runtime when the application starts, so the application can connect to different databases, but in the same way. We have only one option, which is the --Postgres. In that contains a URL with the connection string that encodes the host and port to connect to, the username and password, along with the database and any other options. Using this format allows us to connect with low security to our local dev or test database, but then switch to higher security or different options when connecting to a production server. There's a link in the notes which will tell you the format of that connection string. Back to the main code. And the next block is setup Postgres pull or exit. It passes in a context call to parse config, allowing the connection pull to be configured straight from the URL. But then I override this to have a minimum maximum connection unit and connection lifetime. What this means is that connections once created will be discarded after they've been used for 30 minutes. We then create a new pull that's configured and then ping the database to check that everything connects okay. Finally, it returns that pull. Back to the main, it calls defer pull.close so that the application cleans up properly when it exits. The pulls then pass in when we create the new application structure. Now we've established how our connection pull is created, we're going to skip a whole bunch of code and focus in just on how we use the database inside the app. For our purposes, each API call requires some sort of interaction with the database. So what it's going to do is, at the start of the request, it's going to take a connection from the pull, start a database transaction, then run some queries. If everything goes well, it's going to commit the transaction, return the connection back to the pull. If something goes wrong, instead of committing, we'll just roll back the transaction. That'll undo any changes that have been made. This is a common pattern which helps us achieve the goal of atomicity. Our API call might perform 10 queries against the database, some inserts, some updates, some deletes, but they should all happen together atomically. So we wrap all of the operations in a database transaction, which will ensure that they all happen or none happen. Now we're going to examine the code which we actually use to interact with the database. So it's time to look at the sqlc tool. sqlc is a developer tool that generates typesafe code from SQL queries. You write plain SQL files that contain queries such as select star from inventory where product SKU equals $1. sqlc reads those queries and your database schema and generates Go functions and structures. The generated code handles parameters and results safely, so you don't have to write any of that boilerplate code. The type safety aspect ensures that the correct mapping is applied between Go types and Postgres types at all times. The benefit of using sqlc is it enables you to stay in full control of your SQL while getting the convenience and type safety of strongly typed Go code. Tools like sqlc are worth considering because boilerplate or generated code generally saves you time, is always completely consistent and more reliable than handcrafted code. To use sqlc, it needs to access the database and read the table definitions. And then we get some configuration options when it comes to code generation. All of that's done through the sqlc.yaml file. So let's open that up now and take a look. So the version entry 2, that just specifies the config file format version. 2 is the latest version. Under the SQL setting, that lists the SQL generation targets. Each item describes how to generate code for a given schema and set of queries. So schema, this path or directory, is where your schema files live. That's the create table or alter table scripts. sqlc uses this to understand your database structures and types. Queries. This file or directory is where your SQL query files live. That's where you've got your selects, your inserts, your updates, etc. sqlc is going to read those queries and generate Go functions for each of them. The engine entry specifies which SQL dialect you're using. So sqlc supports a bunch of different databases, and here we're using Postgres. Gen points to Go, so this is telling sqlc to generate Go code. I know that sqlc supports other languages as well. Package specifies the Go package name for the generated code. Out specifies the output directory where the generated code will be placed. SQL package tells sqlc which Go SQL driver to use. So here we've selected PGX version 5 instead of the standard database/SQL. That allows it to optimize some of its code. Database is a URL, a connection string to your local development database. So sqlc is going to use that to connect, validate your queries and infer the correct types. Okay, so now we've got our configuration sorted out. Let's go and have a look at our queries that we're using. Open the queries.sql file. Let's examine the queries we have. All of them are prefixed by a specially formatted comment that sqlc will use to determine what kind of function it needs to generate. The name part will end up being your Go function name, and the suffix, for example, :1, tells SQL what the return value will be. In all of our queries, we're returning a single row, but this could be a value like :many to return multiple rows. You can also specify :exec if no result set is expected. There are many other options available. Check out the sqlc documentation website for more details. So let's examine some of our queries. First of all, our add inventory query. This adds some product to inventory, and if it already exists, increases its stock instead of creating a duplicate. This here is a good example of a single query that performs an upsert. It tries to insert the new row with the product SKU and stock level. The on conflict is triggered if there already exists a row with the same product SKU, in which case, instead of failing the query, it'll update the existing row. In this part of the query, excluded.stock level refers to the value being inserted, and inventory.stock level refers to the current value in the table. This kind of query can help improve your system performance. We know that inserting and updating stock is a common operation, so we want it to happen quickly as possible. By performing one SQL operation instead of two, we've halved the number of round trips between our application and the database server. When we'll examine telemetry in a later episode, we'll be able to quantify exactly how long these operations take. The other two operations, remove inventory and get inventory, are pretty straightforward. I'll leave for you to read them on your own time. The only other thing to note is you'll see $1 or $2, etc. in the queries. Those represent parameters that are passed in. Once we've set up the configuration file and written our queries, we then run the sqlc compiler to generate the Go source code that our application will use. To do that, we can run make sqlc, which calls sqlc generate to generate the code. Let's look at the internal/db folder to see what's been created. Let's start with db.go. It provides a query interface that our applications will use and a db.tx interface to be used by the generated code that we'll use to execute SQL. Note that the exec, query, and query row functions are tailored specifically to the PGX database connection library. To create a query structure, we call new and then optionally call with tx to wrap multiple SQL calls inside a database transaction. There are two other files that are created. First, let's look at models.go. sqlc has generated structures that represent the tables we're querying. In our case, there's only one called inventory. That struct contains fields for each column in the table. Notice how sqlc has automatically mapped the columns to the correct data types in Go. You can define your own data types or have third-party data types that you configure sqlc to use instead of the defaults. The other file that's been created is queries.sql.go. Open that up and let's take a look inside. The first thing you'll notice is that each query we defined has been turned into constants. Where a query takes two or more parameters, sqlc wraps those parameters in a structure, as we can see with the add inventory params. That defines the two parameters using their correct Go types. Lastly, we see the function that our app will use. They all follow the same form. You need a queries object, they take a standard context and the query arguments, and then they return the structure representing the rows returned or an error. The add inventory function calls query row and then using the already defined inventory variable, casts the response values into it and returns. The other functions work in a very similar way. Okay, that wraps up the data layer and database discussion. Thanks for listening, and remember, iron sharpens iron, one man sharpens another. Hit the subscribe button if you want to be notified when the next video is out. In the next video, we'll be continuing our discussion about data from the perspective of how the API consumes data and validates it. Thanks for watching.